All right, welcome everybody, and thank you for joining us for our second installment of Fueling the Future with a focus on hydrogen. My name is Jason Stearns. I am the technical sales representative with CGIS for Northern British Columbia. And I'd like to introduce our guest speaker, Mr. Christian Conesa from Trimteck. And Christian's based out of Coral Springs, Florida, and he's going to be joining us today and presenting on lessons learned from the aerospace industry on control valves. So Christian's going to be taking us through a number of different examples and taking the lessons and experiences they've gone through in the aerospace industry and putting a hydrogen experience onto that example. So just quickly, I want to introduce Christian. Christian is, like I mentioned, with Trimteck, and he's the president. Christian has been a valued advisor to Trimteck since the beginning in 2004. He's designed and implemented their ISO 9001 quality management system and vetting and working with distribution and supply chain. He joined Trimteck full-time in 2011 with a mandate to develop the organization into a scalable player in the control valve market. Christian holds a Bachelor of Science from Boston College and a Master's of International Business from Fletcher School at Tufts University. So a little bit about Christian, and if we can go to the next slide there, please. So before we get started, just a few housekeeping rules. If there's any new individuals that are joining us today for our webinar, we do mute the microphone on everybody so that we can get through the presentation in the time slot we have allocated. But we do really encourage everybody to pose their questions through the Q&A box. So if you click on the Q&A box or hover your mouse over to the bottom of your screen, you'll see that little box there that has a question mark in it. Please just click that box, type in your question, and we will address it as soon as it comes through as the questions roll through. So please feel free to utilize the questions and to interact with myself, Christian, or one of the other moderators with the webinar, and we'd be happy to answer them. So I'm going to pass it off to you now, Christian. So thank you very much.
Thank you, Jason. Thanks for the kind introduction, and thanks to CGIS for giving me the opportunity to chat here. Hopefully, this will be relevant. I believe it will be. The topic of conversation today, from our perspective, as Jason alluded to, is applying lessons from aerospace applications. In this case, we're going to tilt it towards hydrogen, but there are some lessons that we've learned dealing in what are ultimately extremely difficult applications in the aerospace industry, bringing those same lessons learned into industry at large, right? So, particularly relevant now that hydrogen is so prevalent and growing. Just a short bit about Trimteck. We're 20 years old, as Jason mentioned. We've been around since 2004. We're a privately held manufacturer of control valves, specifically in the special service and severe service space. We are a bit of a throwback as an organization. Most all of what we do involves an intense sizing and specification process around a specific set of process conditions, and the valve is a solution as a result of that. All right, so a little lag here. Quickly again, in the value proposition, we pride ourselves on products of extraordinarily high quality. The company really cut its teeth on government contracting in the defense and aerospace sector in the United States, building valves that were unique for ground testing systems at NASA's Stennis Space Center in Mississippi. that quality process that was baked into the organization at that point in time now carries through for every valve that we manufacture. Very quick deliveries, also a point of pride for us. We have a very efficient and quick manufacturing process. Responsiveness to the customer and application support, those are two things that go hand in hand. The valves are manufactured in the United States, and they're cost effective, right? So for what they are, we'll put it that way. Some of our customers, I think, that are most relevant here to this presentation. NASA is really, like I said, it's our cornerstone customer. It's really our almost our original customer for custom engineered valves, and subsequently, as a result of the private aerospace boom. In the United States, we've been fortunate enough to have customers like Blue Origin, SpaceX, Relativity Space, the Air Force, et cetera. But also other, non-aerospace customers that have, that are relevant in some way. Some of them in the power industry. So we do a lot of work with NextEra Energy, which is the second largest utility in North America. And then the industrial gas manufacturers, Air Products, Air Liquide, Linde, et cetera. So the presentation breaks out into three different sections. The first is, what do we mean by aerospace industry valves? I want to disambiguate, what we do versus what companies that make some of these, space-bound solenoid valves do. Secondly, we're going to talk about how we engineer those solutions and what lessons we've learned from working in that field. And then third, we'll go over some of our general service product line or more standard product line and point out some of the design differentiation that we've built into the product. Again, specific to hydrogen in this case, that we have and really are unique in that sense in terms of the market landscape. So first off, what do we mean, or what do I mean when we're talking about control valves for the aerospace industry? Primarily, I'm talking about ground testing, fueling, handling of liquid oxygen, liquid hydrogen, nitrogen presses, methane, et cetera, gaseous hydrogen, gaseous oxygen as well. And really, we're in particular on the testing side, the requirements force you into a situation where you have to design a valve for extreme temperature swings, right? The valve has to be able to go from ambient or sometimes hot, relatively hot temperatures to negative, 323 C in some cases. High pressures, typically these gases are handled at 10K or 15K psi. So 4,500 class valves plus. They have to stroke very, very quickly and very precisely, and they have to achieve tight shutoff in that wide range of temperatures. Very briefly, I want to show this video. Hopefully it'll play. Doesn't. Let's see. Okay. Well, that's our first little technical glitch. This is a Blue Origin test site. So this is what these sites look like. Typically out in the middle of nowhere, either in the desert, in the swamp. And these structures have essentially they mimic the throttling of the oxidant and the fuel into the rocket engine, and that has to be done very precisely in order to capture the testing data they're trying to capture from the engine. So that's what I mean when we're talking about ground testing of rocket engines. One of the things that we really emphasize is any kind of, and this is not an introductory, presentation on control valves, but any kind of conversation around control valves really has to be specific to the industry that we're speaking to, or with which we're speaking, because you guys have different names and a different vocabulary for the applications that you all tackle than say a different vertical market would. So in oil and gas, you have a certain set of common control valve applications, refining, chemical, petrochemical, on down. We're talking specifically today about these Aerospace, which, as I said, high pressure, low pressure, liquid and gaseous oxygen, hydrogen, vacuum jacketed valves, etc. The the way in which valves are, valve purists, and I think CGIS is certainly, I would consider, to be a part of this cohort. Um, People who know valves well understand that there are three categories um, that have been established over the course of the last 80 years, you know, and reviewed periodically. But when you classify valves according to service, we talk about general service valves being in the lower ANSI class ratings of 150 to 600 class, and moderate temperatures between -50 and 650 degrees F. You want non-corrosive fluids, minimal pressure drops, no cavitation or flashing present. Typically, velocities are low enough in a general service application that noise is not an issue either. Standard materials of construction, so carbon or stainless steel bodies, and these are your commonplace valves that are interchangeable and common to a wide variety of applications. Special service is an interesting sort of in between bucket, and we designate special service valves as valves that have higher pressures, so above that 600 class, demanding temperatures, either higher temperatures than the 650 or lower temperatures than the -50. Corrosive or erosive media, challenges, pressure drops that start to become significant. So more than half of the of P1 typically. Mild cavitation can be present, and ultimately, what this means in terms of the valve itself is that you're going to have some special materials selection to deal with these challenges. This is more of a custom tailored suit, right, than the general service valve would be. Most hydrogen valves fall in that middle bucket of special service. Severe service is a term that's, frankly, overused in the industry today. Severe service refers to high pressure drop applications that induce cavitation, flashing, choking, or noise. That's unacceptable to the process. It's either going to destroy the valve itself or destroy downstream piping or what have you. You can have a severe service valve that's 150 class, and that's carbon steel body, right? So those are it's not as cut and dry as say these pressure class or temperature limitations. And in order to tackle that severe service, typically you're seeing a valve that has internals that are designed with some variation of a tortuous path to slow down the velocity of the fluid, and prevent or mitigate the effects of cavitation or noise. Flashing is a different matter altogether. That's typically a process issue and not super relevant to the hydrogen discussion here. But when we talk about, this is a sort of the original valve that I'm referring to with respect to aerospace testing systems or rocket testing systems that we've built, thousands of over the years, but started off with a handful in the late aughts, I guess. And what NASA's issue was here was they had test stands in the middle of the swamp in Mississippi, that had been there essentially since the Saturn V days, right? They'd been there since the space race in the 60s, and been built, I wouldn't say haphazardly, but very quickly, oftentimes using, certainly home built or non-standard valving and equipment. And they came to us in 2007 ish, with the question of whether we could replace some existing um, valves that they had in there, and they had, very awkward face-to-face dimensions. They were, built specifically for these stands, and that we took opportunity with those orders to uh, to study the valves, to improve upon them in as much as we could, um, and and we did, in so much as one of their main problems was repeatability, right? So they would, because these valves are metal seated, in liquid oxygen applications in particular, you're not, soft goods are not favorably or look favorably upon, because you can generate, um, you know bits will come off, say PTFE seats, or and then that could potentially be a significant oxygen fire hazard. So there's a lot of oxygen specific issues around these valves. They have to be metal seated. Long story short, but that metal seating in those old valves from the 60s, that seating would only really be truly tight shut off for 4 or 5 cycles, and then they have to go in and replace this copper inlay that we're using to sort of use a softer plug material. We developed a different brazing process to the plug. Dissimilar metals. The plug is softer than the seating surface, but it's repeatable. So these valves don't are not required to be opened up every 4 or 5 uses, and replace and have the trim replaced. So that was a huge win for NASA. Um, First of all, getting them built, but that improvement was definitely a game changer for them. Um, and these valves have cycled, thousands of times since then, and we've continued, like I said, to build. But they handle um, they handle a multitude of different media, and they have to shut off against all of this media, liquid gaseous oxygen, liquid gaseous hydrogen, at up to or down to negative 425 F, straight to the test article. It's not another example of some liquid oxygen valves on those test stands at Stennis Space Center, and this one is particularly interesting as well. You'll notice this valve is coming out of a cryogenic bath, essentially, during cryogenic testing. I want to mention something that was a valuable lesson for us during the development of all these different sort of one-off custom valves, and that is that the testing requirements. Hydrogen is a notoriously small and slippery molecule, obviously, and um, the test that NASA has sort of devised, over the years, in true sort of bureaucratic fashion, they kind of layer anytime there's an issue, over the course of the last 50 years or however long they've been doing this, they, instead of getting, to root causes, they just add a layer of testing and add a layer of testing. So um, the the um, the test is called the GTO8 test, and it's a bear of a test. It's very difficult. What you do is you dip the valve in a cryogenic bath. You ensure that it gets down to the required temperature, and then you leak test it with helium, with gaseous helium, at maximum allowable working pressure, and the other end of that comes out to a beaker, and it's a bubble. It's a literal bubble test like you would have on a standard, rubber seated butterfly valve, but at wild pressures and temperatures. Right, you're talking about 15,000 psi, oftentimes, um, and you're not, it's got to be truly bubble tight, zero bubbles. Um, and that's an extraordinarily difficult test to pass. But what that proves out is the ability for the valve to seal off in, once all of the um, everything has the thermal contraction that it's going to undergo as it cools off. The tolerance work that we did during this time, in terms of understanding um, gasket surfaces and seating surfaces, plug contours, strokes, etc., figuring out, you know, eh, tightening up essentially tolerances to almost a maniacal, to tens instead of, thousands. True aerospace tolerances are required to be able to handle that. So that's all built into our process for designing a valve like this as a result of that, um, that very difficult, some would say unnecessary, test, but we did learn a lot as a result of those iterations over the course of that time.
Hey,
One of
Christian,
the things you'll notice on this valve, yes, go ahead, Jason. Sorry.
sorry, we've got a question, and maybe you're getting to this, but are you able to share the metallurgy and trim metallurgies of this particular solution here?
Sure. Well, this one that we're seeing here is actually it does have a KELF soft seat. I was just going to talk about that. This is I'll talk about the one, the prior metallurgy in a second. That's an aluminum bronze brazing process, essentially, that happens on the tip of the plug. It's got to be buttered in a very specific way. There's an entire weld procedure that's built around how you actually get the aluminum bronze onto the head of the plug. These plugs are typically Monel, because of the oxygen, not so much because of the hydrogen. They have to be inert. But in the case of this valve, it's you can see sort of, yeah, you can see it better here. There's a little ice that's built up on that crack there, but this is what's called a split body valve. Um, it's a valve that instead of being a single piece body, it's EDM cut into two sections, and the soft seat, or rather the seat ring with a soft seat inserted between that, is sandwiched between those two halves of the body, and then torqued both down. I don't hope you can see my cursor. I don't know if you can or not, but down here and up here. So you have the bonnet bolting, but also there's bolting that comes up from the top that's also cryogenically torqued. And what that allows is for there not to be any other. It eliminates the retainer or the cage that usually goes in a valve like this to hold the seat in place. Um, and the this is another weird kind of NASA thing, but um, someone years and years ago took a seat retainer, not with one of our valves, but with some other valve, and put the seat retainer in upside down in one of these valves, and that caused some chatter. They don't fit together properly. They only fit together properly in one direction. That caused some chatter and eventually caused an oxygen fire. So there, instead of saying, well, let's figure out a way to make sure that the seat goes, the seat retainer only has one way to go in or what have you, they just said, no, get rid of we want valves with no seat retainer. So thus the split body valve, which, by the way, we didn't invent this design. We've just improved upon it. That split body design was very, very popular in the aerospace industry in the 60s and 70s because it eliminated the seat retainer. which would contract oftentimes also at a different rate and leave some additional tolerance if it wasn't just right. So and so this one, it's a long way to get to your answer. This is a PCTFE, so this is a KELF soft seat insert here, because for cryogenic purposes, that's the right choice. Let me rip through a couple more of these quickly. This is an example of another valve that had to have very precise tolerance work done because of temperature swing, but this is in the other direction, right? So this is a valve that's going to deals with very hot air that's actually off the ASME table. So it says it's a 2500 class valve. That's just the bolt pattern. The pressures are far lower, but because of the temperature, the the actual body, as you can see, of this valve is much it's extraordinarily fast. What is essentially a heat sink for very very hot air to displace that temperature. This is a valve type that we build routinely for the commercial aerospace companies, but has also translated very nicely and very easily into some of the hydrogen applications at the air separation folks, right? So the industrial gas manufacturers like Chart or Air Liquide, et cetera. Excuse me. It's a jacketed valve, so you have a vacuum jacket around the body of this valve. It's what's called an extended body valve. So there's no the bonnet sits on the valve up here, and you have an extended the body is extended to take the temperature swing and allow allow the bellows and the soft goods to be far enough away from the cold of the process so that they're unaffected. And this is a top entry valve. It's zero fugitive emissions, which is something we'll touch on in a second. That's very important to deal with hydrogen. Obviously, emissions are a very serious concern. So lots of the applications that we're doing in the private sector right now around hydrogen mandate metal bellows seal valves, as well as some kind of jacketing element. And you have down here you can see that aluminum bronze color brazing of a valve that's going to seat directly onto the body. So this is a seat ringless valve essentially, but very common. Super tight shutoff on a valve like this, class 6 shutoff, and I think that's all I wanted to mention on this valve. SIF ports here for the metal bellows are super important, whether it's hydrogen or anything else. When you have a metal bellows seal, you want to be to identify if there's been any breakage or leakage through there. And the actuator we'll touch on a little bit later, but that the piston cylinder pneumatic actuator or some of the hydraulic actuators you've seen in previous photographs also are definitely helpful when it comes to performance of the valve, whether it's the precision in its stroke or the thrust necessary to generate that class 6 shutoff. Another interesting NASA valve. This is for a GN2 press. We should not spend a whole lot of time on it, but if you have questions about this at some point, let me know. It's a cool valve, and the actuation is really what's really unique about this valve is they're using 3,000 psi motive air pressure because they didn't want to have a hydraulic unit. But we obviously would recommend a hydraulic actuator in a case like this. But again, when you're retrofitting existing systems that are oftentimes several decades old, and you have a customer that's pretty set in their ways, oftentimes you have to make these kinds of concessions. So what are some lessons learned and solutions developed as a result of this? First of all, the organization, hydrogen's a different animal, and we're, let's start there. We're Trimteck as an organization is very accustomed to dealing and frankly weird applications, stuff that's not necessarily in the mainstream of control valve applications. So we found that the muscle that we've developed internally around design and engineering, the way that we trace materials, the way that we can simulate applications, bodes very well, or has boded very well for the private sector. We routinely rely on CFD and FEA modeling because a lot of what we do is just one-off work. This is that aperture valve that we showed you up top, and we ran all sorts of this for the Air Force, and we ran lots of different iterations in terms of design, and also iterations in terms of process conditions, virtually, before we turned a single, did a single turn on a CNC machine. So this allows us the ability to test before we build. This is you can see differential pressure here. Valve velocities, which become very important, particularly in oxygen and hydrogen applications, understanding what the actual exit velocity, or valve velocity and pipe velocity just downstream are, because these are molecules that don't like to see turbulence and impingement. So you want to make sure that velocities are kept to a minimum. This is hot air, so it's not as important, but you get the idea in terms of the visualization of this. And then temperatures are that those temperature swings are really important. This is gas flow. Sorry. All right. Give me a second here. So this is the CFD. The FEA is actually more interesting, the finite element analysis in a valve like this, because that really allows us to understand where our tolerances need to be at any given point to maintain either shutoff or integrity of the packing arrangement, et cetera, guiding systems, et cetera, to ensure that the valve is seating in the exact same spot every single time it strokes, regardless of the temperature. This is briefly our applications and design engineering process. We tend to receive process conditions and delivery requirements from a customer. We run it through a sizing and specification exercise. We have a very robust software that we use to size and specify valves. If an order comes in, it goes through a design process in SolidWorks, and then in ANSYS if it needs to be simulated. That gets blown out to shop floor drawings and bombs, and then manufactured right here in Coral Springs. Our supply chain, castings are the only things we don't do here in-house. We don't have a foundry in-house. We source castings all over the world. Most of the valves that I've shown you here are actually not cast bodies at all, but rather they're fabricated bodies from, usually it's Canadian bar stock actually that we end up using. So it's North American bar stock. Machining, assembly, testing, all with its subsequent documentation. The reason I want to show this slide is because that same NASA kind of documentation and QC QA requirement applies to everything that we build, whether we build a 150-pound steam valve or we build a 45, or a 15,000-pound oxygen valve. That traceability is the same for all those valves. Here's a QC QA. We do a lot of valve cleaning, obviously. There's one of our techs in a clean room. All right, so industrial products and applications. I want to be cognizant of time here, Jason. So let me know if I think we're decent right now. So this, I think, is a useful cheat sheet that I like to show anytime there's a large group like this. This is just a basic valve style comparison. These happen to be our valves, but this really goes for most any valve manufacturers. And what we're doing here is comparing the valve styles based on their ability to handle differential pressures, on their CV, size for size, how accurately they control, what's the rangeability or the turndown you can achieve with the valve, and how costly are they relative to other valves. This is a very broad strokes comparison, but I think it's a really useful first pass. I won't go through each one of them individually, but globe valves are, you've only seen globe valves in this presentation because for very difficult, applications where you're having um, uh, to introduce, whether it's exotic alloys or um, cavitation control trim or noise abatement trim, et cetera, or you need tight shutoff. The globe control valve is really the the pinnacle, and everything else is kind of an iteration of that. They all have their place, they all have their applications, but for what we're talking about, really primarily, we're talking about globes. Let me just go through here. I'm going to talk about each of those individually, but we won't do that. Okay, so two industries that, well, again, there's a lag here. I'm sorry. Two industries that very obviously carry over to the private sector from that aerospace expertise are industrial gases, like I mentioned, and LNG. So the applications that we've tackled in industrial gases go anywhere from the JT valve to cold box applications to low flow, et cetera. And LNG, similar applications, usually lower pressure classes. But you have some of the traditional sort of gaseous applications, natural gas applications like compressor recycle and anti-surge. The OPGL for us is essentially the flagship product framework around which we work for all of these special and severe service valves. Right out of the box, this valve has a piston cylinder actuator, which we'll touch on, which produces extraordinarily high thrust and size for size, particularly against diaphragm actuators. And that allows us to do a lot of interesting things in the body of the valve, that from tight shutoff, but also being able to characterize with the flow with the trim geometry of the plug head as opposed to the geometry of a cage. We manufacture these in globe style, angle, three-way, etc. All different sorts of end connections and all different materials. So first and foremost, that piston cylinder actuator, that coffee can actuator that you saw out there, which is our standard pneumatic device, allows you to do a really interesting thing in the body of the valve, which is remove the requirement for balancing in most applications. So what the most effective way to control flow is with the geometry between plug head and the seat ring of any valve, right? As this valve strokes, then you get your flow characteristic, whether it's equal percent, linear, or quick open, or bilinear. It allows us to pack the packing box tighter. Okay, so because we have additional thrust, we can overcome more friction in the packing box. That gives you better emissions control out of the box. Again, important for hydrogen as well. Hydrogen specifically, we'll talk here. We talked briefly about materials and tolerances, material selection. For the temperature swings, that's an important consideration, but really what narrows down the material selection in a hydrogen valve in particular is HE or hydrogen brittlement, which is presumably you guys know what that is. It's a process that happens to particularly hard substrates. Typically, the guidance that we use for, in particular, gaseous hydrogen applications are 316 stainless steel with a minimum of 12% nickel content. That's what we like to use. It's soft enough to discourage hydrogen embrittlement, um, and uh, and it's it's machinable, it's commonplace, et cetera. There are other materials that can be used, but but primarily when we're talking about bodies, it's 316. Um, the body configurations can go from anywhere from a T style straight through um, body valve or standard flow through body valve to Y pattern valves to angle body valves, and then what we call the OPGL XT, which is a bar stock body variation of this, and which is a lot of what you've seen in the slides above. This configuration is identical, so the bonnet, plug, everything about the internals, all of the dimensions are identical to those of a fast body valve, but with a fabricated body, you can do some interesting things around tolerances. You can do some interesting things around just face to face material selection, etc. So we find this to be the most versatile way. It also helps to improve deliveries dramatically um, as well.
Christian, we have a couple questions.
Sure.
So the first question is, what kind of lubricants are used, if any?
So that's a good question. Typically, Krytox is what we are. There's typically no lubricants inside the valve. There's nothing. There's no requirement for anything like that. Typically, instead of anti-seize or liquid graphite or what have you that you would use to thread the plug stem into the actuator stem, you're using Krytox grease, which is oxygen rated, but it from NASA's perspective, and those requirements are the hydrogen requirements are identical. So Krytox, it's extraordinarily pricey, but it's what's required.
Thank you, Christian. The next question is, what are some of the main differentiation points between the OPGL valve and say the Fisher globe valve or a FlowServe Mark 1 globe valve?
Sure. So there's two different answers there. So um, there are, I would say there's two schools of thought in the world of control valves around actuation and guiding, right? So you have the Fisher traditional Fisher E-body valve is a fine valve. It also happens to be about 130 years old in terms of a design, and its guiding system is in the body in the cage of the valve, and that allows them to use a diaphragm actuator that has um, you know frankly size for size a lower thrust than than a um, than a piston cylinder actuator would. So that there's a lot of differences between the standard Fisher style valve, E-body valve, and the OPGL. Between the Valtech Mark One and our valve have many, many more similarities. That is, we both subscribe to that top guiding. They were the innovators essentially of that top guiding system of using strictly a piston cylinder actuator to move a top guided or double bonnet top guided um, uh, stem in a valve and allow you to control with the geometry of the plug head instead of a characteristic, carved into the side of a cage. They are, we certainly as we were building out the more general service product line, um, we're inspired to some degree by that school of thought. The Mark One and this valve are similar, but there is no there's no interchangeability. There's nothing of that sort between this valve and that. Um, I would say we both belong to the same general school of thought um, in terms of the world of control valves. We also do a lot more in terms of customization, both in terms of materials, um, trim sizes. Uh, we fall into that special and severe service bucket a lot more than those companies do, mostly as a product of their being, owned by large conglomerates that are not really super keen on you know low volume unique applications. Um, so that's the answer to that. Um, Let me move on down. So we have there's your um, guiding system. So when we talk about guiding the plug stem, we're guiding it in two spots over 2/3 of its length. Top guide, lower guide, and then packing sets in between. Those packing sets, packing. We haven't touched on this yet, but for hydrogen, soft goods material selection is important as well. Uh, Selecting the right material for gaskets, and this, you have all the standard considerations around temperature and pressure, but also there's a permeability element. Hydrogen finds its way through lots of different solids. So typically some kind of reinforced PTFE will be better than virgin PTFE, although virgin PTFE is used also in very high pressure valves. So there's a little bit of an art there to selecting the proper gasket. We've done everything from spring reinforced PCTFE gaskets and PTFE gaskets to graphite in some cases, standard graphite packing and gaskets. Let me jump through here. I want to point. Let me see if this is probably a better one. So this is a unique, talking about gaskets, talking about permeability in terms of gaseous hydrogen. There are the two most important soft goods outside of the packing set, obviously here, in terms of the valve body of the shell, are the bonnet gasket and the seat ring gasket here. Here's a useful little chart for identifying the temperature and pressure limitations of various gasket materials. But I want to point out here that one of the most elegant design features of this valve is somebody asked about Fisher. Fisher's valves are typically balanced, which means that this plug would have an additional soft component required to slide, within the cage. So you're adding an additional point of permeability, additional leak point, whereas this valve only has two. You can either leak out of the bonnet gasket or leak through the seat ring gasket. Against the tolerance and the compressions, the compression here has been over the years very, very tightly calibrated to make sure that compression works for negative 323 F and also 100 degrees F. So those temperature swings are super important. Here's the soft seated variation of the seat ring. A true plastic soft seat, as we're talking about. This is either PTFE or PCTFE seat ring that sits in the middle of the two, or sandwich in the middle of the two metal seat components, and that's what can give you bubble tight shutoff in terms of leakage. Flow characteristic built into the plug head. I won't spend a whole lot of time on here, but that's a huge differentiator between this valve and the traditional, e-body style valve that's very common out in the marketplace. A range of trim configurations. So because of this design, every size iteration of the OPGL has essentially an infinite number of different trim sizes that we can mechanically machine between the smallest, and it does go smaller than this. There are microflow trims that are further reduced than this, all the way up to full port. So you can really mechanically home in on the characterization that you're looking for. Here's a quick trim material comparison. Um, and I want to point out again, I assume you'll have access to some of these slides, so you can go ahead and look through that. If you have any other questions, you can let me know, but I won't go through the table. But I do want to touch on CVD 5B, which is a process that we use for hardening against erosive. It's designed for erosive surfaces. It's a chemical vapor deposition process using boron. But in the case of hydrogen, there are companies that have, asked us to do, for cost saving purposes. We don't want an all 316s, stainless steel facility. You're buying 100 valves, 1,000 valves, whatever it is. The price difference between a carbon steel body and a stainless steel body can be very significant. If you apply this chemical vapor deposition process to carbon steel, it increases the resilience against hydrogen embrittlement. So this is a really interesting sort of additional layer of protection that you can put on a substrate to help prevent hydrogen embrittlement over the course of its lifespan. Here's your different bonnet extension
Christian,
configurations. Yes.
sorry, question on the previous slide. How's the permeability on the boron coating you spoke about with hydrogen?
It's how do I put this? There's no permeability. I mean, what you're talking about here is hydrogen embrittlement, and you're preventing that because this is you're creating a very thin new layer with a new metallurgy that's going to prevent the molecule seep. Embrittlement happens because the H2 molecule will break up, and single hydrogen atoms will find their way into the metal, and then in some cases find another hydrogen atom and rematerialize as hydrogen embedded in the substrate. This has been shown to be able to reduce the permeability. If you want to technically permeability, but it's like permeability. Severe service, very briefly, slowing down the velocity, in particular when we're talking about gases, very important. So there are noise abatement tools or cartridges that we use that also obviously drag down the velocities going through the valve. In cases where you have liquid hydrogen or liquid oxygen service, or any liquid for that matter that's cavitating, there's a similar phenomenon at play, but you're trying to prevent the pressure drop from exceeding or breaking through the liquid vapor pressure. So you stage the pressure drops accordingly. There's your piston cylinder actuator. Very quickly, I want to be respectful of time here, and I apologize. I feel like I've gone a little longer than I anticipated, but this is a very sort of what is now a very run-of-the-mill valve for us, but you could see that it comes very, very directly. There's a direct line from the valves that we were doing for NASA to this valve for Air Liquide. Mostly, this is for oxygen service, both ambient and liquid, but they're looking at hydrogen applications as well, and the valve would be not dissimilar to this. Potentially, it would have metal bellows seals and a vacuum jacket as well. the the Now this is a good example of a valve that's, one for one. We're taking experience from hydrogen service in the aerospace industry and bringing it directly to the private sector, or rather the industrial gases space. Um, as you guys may be aware, as this hydrogen value chain kind of grows and expands, and people experiment with different downstream applications, and the electrolyzer, the sort of green hydrogen piece is pretty well figured out, in terms of material selection, pressure classes, etc. Downstream is becomes a little bit more interesting in terms of what people are, or what companies are trying to do. I've in some cases, um, trying to figure out how you're going to transport bulk high pressure, um, hydrogen gas, and potentially, you know, use that to fuel a vehicle fleet or whatever it is you're doing. Um, at the volume you need to do that effectively and economically, um, most most valving and most piping, frankly, that's built for that pressure range. You're talking about 15,000 psi to 20,000 psi in some cases. Um, is 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 very, very small ports, right? We're very accustomed to. There's a whole industry around, 3/8 inch, um, or three tiny, ports, and tiny instrumentation essentially for these very high pressures. Scaling that is where we come in, right? So we're working with a company now we've built a series of these smaller valves, and are using a lot of that knowledge gained through the aerospace testing applications to figure out how to build, what tolerances, what body, what pressure vessel dimensions and things like that, um, to build into, say, a 2-inch line that's going to handle 2,000 or 20,000 psi. That's a very different proposition than a 3/4 or a 3/8 inch line. Um, Material selection, though, we have, very much down pat, and that's a good portion of the way there, for these valves.
Christian, we have a question on any guidance on tolerance selection. I'm not sure if you need a little bit more context or not, but
I imagine, the attendee is asking about tolerance selection within the valve. Presumably, material, dimensional tolerances, within the plug, the seating surface, etc. I don't know that there's a rule of thumb. If you're interested, I could potentially put you in touch with one of our design engineers, um, and maybe he has something to add to that. Um, I think they're working on some kind of general guidance, with a table with pressure ranges and temperatures, and sort of figuring out where they're going to be from there. We probably have that internally in terms of a work instruction, but I think that's probably something to discuss offline. So I'm happy to you know to put you guys in touch, um, if that's something that's interesting. Um, I'm sorry that doesn't
thanks,
answer
Christian.
the question, but frankly, I don't have the answer, but I can get it for you.
Yeah, we'll connect.
The
We'll connect with the individual offline. Thanks.
Yeah. So in some cases, this is a boiler feed pump recirculation valve, um, and this is not necessarily related to hydrogen. Well, it's not related to hydrogen at all, but just the process by which we go through and design a valve. This is an application that's fairly commonplace in most combined cycle plants, but it's also very susceptible to failure. Lots of the tried and true control valve manufacturers, all of whom are extraordinarily capable, and have excellent products, often fail more than they should at these applications. And really, we've found that it really comes down to the approach that we have of understanding very, very closely what the application is, and then building a solution around that. So, in this case, it was a very, very high pressure drop application that produces a flashing condition, which was essentially ignored by most of the previous folks who attempted this application. And we sort of cracked the code, but it's not. I guess my point here is it's not magic. If you put an application through this system, typically the answer will be some solution that's scalable and applicable. Um, work my way down. I'm going to skip a couple of these, um, and jump to the last slide. So, considerations for hydrogen valves as a wrap up. Um, you know, things to keep in mind: temperature swings. So material selection is super important for that. And understanding obviously what the thermal contraction or thermal expansion looks like in the valve as a result of that. Between the valve and the pipe is another important consideration. Tolerances, again, that's a lot of. We have the enormous benefit of kind of having this Formula One team in the aerospace industry that's done a lot of trial and error around tolerances at different temperatures and pressures. So we have a lot of expertise in that in that selection process. Embrittlement is something to definitely keep in mind, and that informs material selection for both soft and hard components. Again, the rule of thumb that we use is 316 stainless steel with a minimum of 12% nickel content. Really, to be called 316, you only need 10%, but the 12% is empirically has been found by us and other valve manufacturers to be more resistant to the embrittlement. Soft components as well, equally important. Fugitive emissions, we touched on that, but obvious. I mean, I guess I don't know how obvious it is, but hydrogen coming off the top of out of the top of your valve is not a good thing. And so your metal bellows seals, the material selection in your metal bellows seal, they have to be hydroformed metal bellows if you have a control valve not welded. Because if you have a control valve in a system like this and it's stroking frequently, the hydroform metal bellows seal will be far longer lasting. You're talking about millions of cycles as opposed to, in some cases, just thousands with the welded. Jacketing these systems is usually a best practice for fugitive emissions purposes. And then tight shutoff, whatever performance you're looking at of the valve, obviously you have those considerations. We've figured out how to develop innovative soft seat materials, both in sort of hard seat components with cladding and things of that sort, as well as with PCTFE and PTFE. So I apologize for going over. I hope this was somewhat informative. Certainly, reach out to CGIS or myself with any questions. I'm happy to discuss this further with whoever would like to do that.
Christian, thank you very much. We've got a few questions here. Folks, we have exceeded the time, but we will stay online here to answer all the questions, and also stay online to have the opportunity for folks to add additional questions based off some of the responses that Christian may answer here. So we'll stay online as long as required. A copy of this presentation is available. A recording will be available and sent out to you from our host Sam Wynn, and he will also be able to provide a certificate of attendance. So for those individuals interested in having a certificate showing their attendance to this webinar, please let Sam and the team know with the email that he'll be sending out later today, and we can make sure that you get that PDF copy of that certificate. Off to the first question, Christian. So, what are the main concerns in a control valve selection and design when it comes to hydrogen?
So I would say material selection for hard and soft components, as I said. I mean, well, maybe we back up. So uh, you always want to have process conditions when you're quoting, or when you're putting together a solution for a control valve. So your upstream pressure, your downstream pressure, flow, temperature ranges, etc. Um, that's sort of 1A. You need, in our opinion, you need that for any control valve, proper control valve sizing and selection. With hydrogen specifically, when we know what state the hydrogen's in, whether it's liquid hydrogen or gaseous hydrogen, understanding what the fugitive emissions requirements are, right? So, does the valve, where is the valve going to be? Does it need to be jacketed? Ergo, does it need metal bellows seals? If not, then what kind of packing arrangement, what kind of packing materials are you going to be using on this valve? Do we need to live load that packing? Meaning, what's the fugitive emissions rating we want to give this valve? And that can frankly vary from customer to customer, but those are just things to keep in mind as you're specifying a valve or any system that's going to run hydrogen. It's the sneakiest of molecules, we'll put it that way.
Thanks, Christian. The next question. Valve standards for hydrogen applications seem to be relatively unknown at this point. Are there aerospace standards that might be useful that can be applied from that industry to hydrogen?
That's a great question. I think so. I know that MSS Committee 410 is working on a hydrogen standard for valves, and that's due out any moment. That's the working group, by the way, within the MSS that handles severe and special service control valves. So those two categories we saw at the beginning of the presentation, and I know they're working on a hydrogen valve spec, which will guide some material selection, I assume, and that kind of thing. Whether there's a direct aerospace correlation, that's a difficult thing to answer, primarily because the aerospace companies themselves don't even abide. It's not that they don't abide by it's, NASA is a big, heavy government entity that, requires an unbelievable amount of documentation, empirical evidence. So they are on one end of the spectrum. Whereas if you see a customer like SpaceX or Blue Origin, who are out to move quickly, and it's obvious that they have, right? They will sort of cafeteria plan the specifications to some degree, right? To some of which we kind of give pause and say, hey, this is I don't know that this is really the right way to go about doing this, and we'll be very straightforward with the customer if it's a private sector customer. But there are some things like the GTO8 test is a test that's frankly a little dangerous if it's not done properly. So we've seen, it's a hard question to answer because even within the aerospace world, there isn't really a standard that everyone abides by for valves that like this, for ground system valves. I don't know I think there may be an analog potentially with respect to valves that are space bound that are actually on board. Although, I mean, I feel like we would be seeing those as well. So I don't know. I don't know. We've kind of accumulated as an organization. Trimteck has accumulated a lot of a lot of the different standards and a lot of the different sort of tribal knowledge around this stuff. And whether that, obviously that's not an industry standard, but it is translatable, to some degree. Uh, but really, I mean, I think if nothing else, take away the fact that an H like a hydrogen valve selection and sizing is not to be taken lightly. It should be handled with the same approach as someone building a lethal service valve or an aerospace valve or something um, where you want somebody to be able to take those process conditions and then run them through a bunch of different checklists and simulations if necessary to to make sure that you're dotting your I's and crossing your T's.
Thank you, Christian. The next question we have here is, what recommendations would you make when it comes to plug design for a hydrogen control valve? And are there preferred styles versus others?
So plug design. Um, so we favor an unbalanced, you know, top guided plug design, like I've shown you, where the geometry is built into the plug head. Um, I I think within the aerospace industry, any of the applications that I've just talked about, they stay almost fanatically away from balancing valves, because balancing the trim in a valve, um, you're introducing a whole other ecosystem of potential failure points in a valve. Um, and when you're dealing with thermal contraction and thermal expansion to that degree, you're dealing with sometimes permeable soft goods and all sorts of other you know laundry list of things to worry about. Um, Using an unguided, unguided, or not, I'm sorry, a top guided, unbalanced plug design is certainly the way to go there. Um, if for nothing else, that it removes lots of extraneous components from your system, so the reliability will be increased.
Thank you. The next question, do you take any different approach in the machining or finishing process to work with the with hydrogen since it's a smaller particle?
Uh, that's an interesting question. I think, well, yes, I mean, we do some. Um, our tightest tolerances are in oxygen and hydrogen. So the machining process doesn't really change. There may be some finishes, electro polishing that happens for to ensure that there's the right surface finish, either in the body gallery of the valve or on the trim itself. Um, so that's more common in ultra high purity oxygen applications. Um, but whether we would do anything with hydrogen specific, the finishes and all these components are typically satisfactory, kind of off the machine, even if it was for a general service product. Let me see if there's any other additional points to that. No, the tolerances are, yeah. I mean, we will run a different plug program on the CNC if it's for a valve that needs to be in cryogenic service, right? Because the tolerances have to be that much tighter or looser in some cases. But
Yeah. Okay, awesome. And the last question we have here, which I think you may have answered earlier in the presentation, but might be a good refresher, is there a preference between forged body and castings when it comes to hydrogen?
I don't know that there's a hard and fast rule. We we just end up using more fabricated body castings. I don't know that we've sold a handful of cast body um, valves into the hydrogen space. Um, Typically because of the temperatures, because of the fact that oftentimes these valves um, will seat. There won't be a seat ring; they'll seat directly onto the body of the valve. It is easier from a manufacturing perspective to fab those out of bar stock or billet, but I don't know that there's a hard and fast rule. That might be a question for our design and our design engineering group. And there's specifically the guy that handles metallurgy. He might be able to see if to give you a definitive difference in terms of the molecular structure of a forged F316 versus CF8M or something like that. But I don't think there's a hard and fast rule off the top of my head, nor is there a recommendation, I think, from our end, one way or the other.
Wonderful. Christian, thank you very much. Thank you for the outstanding presentation. I know I found it very educational and insightful. Uh, I don't see any more questions coming in, so if there's no other questions through the attendees that are still online, we'll leave the queue open for the next 30 seconds here, and we'll send everybody off on the rest of their day. And please enjoy your weekends and stay safe. And thank you for attending.
Thank you, guys.
Thank you, Christian.